Hi, we've got a 19-inch TFT monitor on the bench today, so a family member brought this round because they kept having to replace the fuse in the mains plug, and eventually they've replaced it one final time and the monitor is no longer working. So we're going to have a look inside the monitor and see if we can diagnose what the fault is and then see if we can repair the monitor. When something presents itself as blowing the mains fuse, we're typically going to look at a completely different range of faults as opposed to if the monitor just wasn't powering up. So the switch mode controller that's in the switch mode power supply is very unlikely to blow mains fuses if there's any kind of fault on the secondary side of the power supply. So it's almost certainly going to be something very early on in the switch mode power supply, maybe around the chokes or the filter capacitors, or there may even just be some dirt on the power supply that's allowed the input mains to short across a carbonised track. So let's have a look inside the monitor and see what's going on. So this is a Benq FP91G Plus, manufactured in July 2006. So if we manage to repair the power supply, it's probably going to be worthwhile changing the capacitors in the power supply as well, because they're getting on for 10 years and it's probably got quite warm at the back, so those capacitors are going to start drying up. But we'll be able to use the Peak Atlas ESR meter just to check those capacitors. So I'll just take the back cover off and we'll have a look at the power supply. Right, so we should be able to whip the cover off now. And now we've got a metal shielding case inside, so that's nice. Can't see any screws around the outside. It probably just wants these undoing. And that seems to have loosened that off. I just need to take off this connector from the front menu buttons. So there's not actually a great deal inside this monitor. We've got the power supply on the left and then the actual controller board on the right. So let's take a look at the controller board first. Here we have the controller board and there's really not a lot to it. So at the bottom left here we've got the DVI interface, we've got the VGA interface on the bottom right, and then we've got the connector which goes off to the front panel connector and the flat flex cable which goes off to the LCD panel. And then just on the left hand side here we've got the cable which comes from the power supply board, and presumably there's a couple of supply rails and then some control signals going back for the backlight and to put the power supply into standby mode. The level of integration that's going on here is really quite high, so really all there is just this main chip here, which is a Realtek RTD2523B, and this is a complete flat panel controller, and it has a 3-channel ADC for the RGB interface from the VGA connector, and then it also has a DVI interface so that this can just interface directly to the controller. We've got a whole load of 3-pin devices here, so these are probably protection circuitry to clamp any excessive inputs on the input here to the supply rails. And then we've got a crystal here which is a 24 megahertz crystal. And then we've got 3 8-pin SOIC packages, so these are Atmel EEPROMs. And there's one next to the DVI connector which will be to identify the device that's on the end of the DVI cable. So for example, if you've got this plugged into a computer, it knows the capabilities of what this display can actually display. And then we've got one up here which seems to be routed towards this Realtek controller here, and we've got one here which seems to be running into the chip that we'll have a look at here. This little IC, which is sitting next to the 24 megahertz crystal and the flat panel controller, is a Myson MTV512, and this is a microcontroller that has an 8051 CPU in it, but it also has a few interfaces for running in display systems. So it has a Visa compliant DDC interface for communicating with the PC and the flat panel controller, and then it also has the usual kind of things that you'd expect to see on a microcontroller. So it's got some PWMs which could be used for the backlight controller, and then various IOs and interfaces to RAM if you were to have a controller that required external RAM. And then the SO8 packages, of which there are 3 on this PCB, are 24CO2 2-wire EEPROMs, and these just have 256 words of storage on each one. So here we have the power supply board. So we've got the IEC connector coming in with a nice earth wire going to a crimped ring terminal going to the chassis of the monitor. We've got some filtering capacitors at the inlet. We've got a fuse, which is a 2 amp fuse. We've got a common mode choke, bridge rectifier, a nice big capacitor which is on our primary side, so that's our main reservoir capacitor. Then we've got our switch mode power supply transformer, the controller, and then we've got the main power transistor which is driving this transformer. We've also got the high voltage section for the CCFL tubes, and actually it could be something here, it depends how they configured it. They've got an isolation gap all the way through here, so it looks like these could be powered from the low voltage side of the secondary of the flyback transformer that we've got here. And then we've got a few, these are diodes here mounted on a bit of a heat sink, and we've got our capacitors here for smoothing, some filtering, pretty run of the mill. It's Benq branded, so we'll take this board out and have a closer look and see if we can diagnose what's wrong. So always remember when you're dicking about with these switch mode power supplies that you just double check that all of these capacitors are fully discharged before you put your fingers on any of the components or underneath the board. So we'll just double check that this capacitor is fully discharged, which it is, and just check that these film capacitors on the inlet are discharged, because they have a very low discharge rate, so they'll keep charged for quite a long time, although I expect these to be fully discharged, which they are. So I'm struggling to see anything in particular which looks faulty on the board or looks to have burnt up. So we've got a fairly traditional front end on this switch mode power supply. So we've got our mains inlet here, we've got some filter capacitors, we've got an inline fuse which we'll check in a moment, we've got a varistor, we've got a common mode choke. The varistor is probably limiting the inrush current through the bridge rectifier when it's charging the capacitor for the first time. And then we've got a few passives. We've got our switch mode power supply driver and the MOSFET for driving the transformer, and then we've just got our feedback opto isolator just here. So this is all fairly standard, and I would expect if there is a fault with this board, it ought to be contained within this barrier here on the primary side, because as I said, the secondary side is going to be current limited by this switch mode regulator. So the switch mode controller in this power supply is a relatively run-of-the-mill on-semiconductor NCP1200, and this is just a PWM current mode controller, and the 40 at the end of the part number just means that it's running at 40 kHz. So the way these switch mode controllers normally work is they derive their power from the 350 volts DC supply through a resistor into one of the pins on the chip, and then also they'll have a pin that goes to ground. There'll be one pin which drives the MOSFET, probably directly, and then there'll be some feedback circuitry, so the opto isolator will form part of the current feedback, and it will just cause the controller to adjust the duty cycle to keep the output voltage on one of the windings of the transformer regulated. And the main transistor used on this switch mode power supply is a 2SK3530, which is a 7 amp N-channel MOSFET, and it could be that this transistor has gone faulty and gone short from drain to source, which would mean that we're getting full current through one of the windings on this transformer, and it could blow the mains fuse, although I would expect it to blow the fuse that's on this board. And the transformer used in this power supply is also relatively run-of-the-mill. It seems to be nicely constructed, Probably oversized for the application of this particular monitor, but it's quite likely that this power supply is used in a whole range of monitors, not only by Benq but probably LG and a few other brands as well. And then we have the photocoupler here, which is an 817A, and this will be a transistor output optocoupler because the switch mode power supply is running on current mode feedback, so we'll probably find a TL431 reference on the board somewhere, which will be allowing this to work in current feedback mode. And then here we have the main bridge rectifier, which is a 2N357, and this is rated for 2 amps at 600 volts, and this will be rectifying the incoming mains and charging the main filter capacitor on the primary side of the switch mode power supply. And here we have the common mode choke, so this will be after the filter capacitors on the inlet, still passing AC at this point, and you can see one winding here and the other winding here. So these will be both wound in the same direction so we get some common mode noise rejection. We'll then probably see that the current passes through this varistor into the bridge rectifier and then charging the main bulk capacitor on the primary. And you may just be able to make that out there on the capacitor. The rating is 100 microfarads, 450 volts, and that's our main bulk capacitor on the primary side. And other than the Jamicon capacitor, which is sitting next to it, almost all of the other capacitors on the board are made by Elite, but I've never heard of that brand before. And the big film capacitor here is a 470 nanofarad MKP X2 capacitor, and this is just on the AC supply straight after the IEC connector, just for a bit of noise suppression. And then we have a couple of big 2-watt power resistors here. So one of these is probably supplying the switch mode power supply chip, so it'll have the 350 volts DC coming in, then it'll be dropping some power in the resistor and then powering the chip directly. And then there'll be another 1 or 2 resistors which will be limiting the maximum current through the switch mode transformer. So let's just test this mains fuse, which you can probably just about make out is connected to the phase pin on the IEC connector. This is a 2 amp time delay fuse, so the T means it's time delay. If it said F, it would be a fast blow fuse, and the time delay just means that it's rated for short surge currents so that it doesn't blow when the main reservoir capacitor has the big inrush current when you first power it up. And it's also nice to see that this is a ceramic fuse, so if it does go bang, it's not going to explode everywhere. The ceramic will hold the fuse intact. So let's just test this. And that fuse isn't actually blown, so that's quite interesting. I probably should have powered up the monitor before I took it to bits, but it's surprising that that hasn't blown if it's been blowing the mains fuses, although the fact that it's a time delay fuse may mean that the fuse in the mains plug may have a chance of blowing first before this one did. So here we have the underside of the PCB around the primary section, so you can see the isolation barrier here with the black line. And again, there doesn't really look to be anything obvious wrong. So there's one gouge out the PCB here, but if that was causing a problem, especially right next to the mains inlet, you'd be expecting to see a bit of carbonisation of some of the tracks if there had been a flashover or anything like that. There's a bit of dicky soldering, but nothing too obvious. So at this moment in time, I'm either suspecting the main power transistor here, which is driving the transformer, or the transformer itself, or maybe possibly one of the filter capacitors which is right at the inlet to the IEC. So it is possible that these capacitors have failed short, but we'll have a look at that in a bit. And I'm not sure if you can make it out, but there's a very small amount of discoloration of the PCB kind of around here. It's quite difficult to make out on camera, I think, but there is signs of the transformer getting quite warm, although if there was anything where the transformer had started to overheat to the point where windings were shorting out, I think you'd see quite a bit more damage than just the kind of discoloration which you can see along here. So you can see a little bit of the slightly dodgy soldering going on here. This resistor's not the best, although it's not really going to be causing any issues with overloading of the mains supply. And then there's the odd solder joint like this one here, which is definitely a very cold solder joint. you can really see that it's not bonded to this wire at all very well. So we'll probably touch up some of the solder joints, but I think we may just need to power up the LCD monitor and just see what it does, and then we might need to start taking a few measurements. And we've got a couple of instances of this around the PCB, so we've got a really dodgy bit of soldering going on here. These pins are almost touching, and this pin looks to be another cold joint. So I might just run around the board with the soldering iron and just tidy up the soldering a bit, but then I think, yeah, we definitely have to power up the monitor and see what the fault is. So we'll just tidy up some of the soldering on the PCB. And just while we're here, we may as well test this film capacitor, which is just on the inlet to the mains, just in case that was faulty. So I'm going to use the Peak LCR45, which I'm going to review in a video in a few days. So we'll just check what the capacitance of this capacitor actually is. And that's reading 378.7 nanofarads, so that's exactly within range. It tested that at 1 kilohertz, so that seems to be fine. I did wonder whether it had managed to fail short, but it seems to be fine, so we'll solder that back in. And then we can just give the PCB a quick clean to remove any of the flux residue. So we've got a bit of flux clean here. We'll just spray it on the board and give it a brush to get the flux off. And whenever you're using flux remover, it's always worth putting some tissue down or something and brushing the PCB through the tissue, because we need to absorb the flux residue into something rather than just wiping it onto a section of the board wherever the flux cleaner happens to dry up. And here we have those two 3-pin diodes which were looking really dodgy before. Those are looking a lot cleaner now. While we've got the PCB out of the monitor chassis, we may as well just check the ESR of some of the capacitors around the circuit. So I've got the Peak Atlas ESR70, which I reviewed in an earlier video, and this can measure the ESR of the electrolytics while they're still in circuit. So we should be able to turn this on, and we've got the main capacitor just across these two pins here, and that's measuring 105 microfarads and 0.6 ohms, which is pretty good for getting on for a nearly 10-year-old monitor. So that electrolytic's fine. We've got a couple of electrolytics here, so I'm assuming one of these is providing a bit of smoothing for the regulator IC, so we'll just check this one here. This is a 47 microfarad 50 volt capacitor, and that's connected across these two pins. And that's 43 microfarads, 0.57 ohms, so that's got a nice low impedance value. And then we've got another electrolytic here. This is identical to the one that I've just tested, so we'll see what that one reads as well. And that's pretty good as well. So I think that's all we'll do with the board while it's still out. It could be worth just checking this MOSFET here, but I think I'll stick it in the monitor first and we'll power it up and see what happens. So I've actually just managed to find a service manual, not for this particular Benq monitor, but the schematic for the power supply section looks very similar. It's not quite the same, But we've got our IEC inlet with the 2A fuse and the filter capacitor here, with some 510k resistors to discharge that capacitor. We've got the common mode choke. This one has 2 on the schematic, but we've only got 1. We've got the bridge rectifier and the main reservoir capacitor, which is that 120 microfarad 450 volt capacitor. And then we've got the regulator chip, and you can see this is powered directly from that 350 volt DC supply through an 18k resistor straight into the power supply pin on this chip, and then we've got ground down to system ground, and then we've got 2 windings on the primary. I can't remember if there were 2 windings on this particular board. We've got our main MOSFET for driving this winding. They've deviated slightly from the standard way of driving the MOSFET, because these normally have quite a good gate driver in it, but they've basically got it set up so that when you turn on the gate of the MOSFET, it's coming through this 47 ohm resistor, but when it's turning off, the gate charge can go through this diode and straight into the gate driver on the DC to DC converter through this 4.7 ohm resistor, so they can get faster off times for the MOSFET. And then you can see we've got the opto isolator here. This one's got a TL431. I didn't look on the board to see if there is one, but that's normally the standard configuration for one of these chips. And basically what it's doing is just sensing the voltage on the secondary side and passing that through the opto isolator back into the feedback pin on the DC to DC converter chip. And then there's also some current sensing on the primary side through this 0.22 ohm resistor, which is going into this pin here, so that it can measure the current through the winding. And then just on the secondary side, you've got a fairly standard configuration here. So we've got the rectifiers here and here for this winding, some bulk storage capacitors and a bit of filtering, and any additional regulation required for different voltage rails. And the feedback is taken from the main winding, which is probably driving all of the logic. And then just using the knowledge of the turns ratios, you can derive any other power supplies just by adding additional windings to the transformer. So I've now connected a mains lead into the monitor and loosely put the cover on. So let's power it up. We've got the power switch at the bottom right here with space for the indicator LED. So hopefully we'll see that do something if it's working. Unfortunately, I didn't actually try it before taking it apart, so we've got nothing to benchmark it against. And I'm really hoping it wasn't the mains lead that was at fault or something like that. I don't have the mains lead that was being used with this, but there is a potential that it was maybe crushed or damaged, and indeed it was just the mains lead which was causing it not to work. So let's power it up and see what happens anyway. So it's now turned on at the mains. We haven't got anything on the front panel yet. I don't know if this is a bi-colour LED or not, but we'll turn it on and see what happens. Okay. Well, it didn't go bang, and it still seems to be powered up, so it's not blown any fuses yet. So I might just hook this up to the power meter and check that the current consumption's normal, and I'll also hook it up to a signal source so we can see what it's doing. So I've powered up the screen and I've connected a computer to the VGA port, and it seems to be displaying everything perfectly fine. Let's have a look at the power meter and see what the consumption is. So we have the power meter here displaying the incoming voltage, which is 242 volts. We've got the current being drawn, which is 0.2 amps, and then the number of watts, which is about 32 watts. And the power factor of this monitor in its current configuration is 0.64. So we can also have a look at the oscilloscope and have a look what the waveform being drawn from the mains looks like. So here we have a waveform of the power being drawn from the mains by the monitor, and the horizontal is set up for 10 milliseconds per division. So we're seeing these current peaks at 10 milliseconds, which is the equivalent of 100 Hertz, which makes complete sense. So there's no power factor correction in this monitor. We saw that it was just full wave rectified and then charging that big main capacitor. So what we're seeing is the current being drawn in pulses as it charges that capacitor on both the positive and negative cycle of the AC waveform. So this is with the monitor at full brightness, and we can see that the current is just peaking at slightly over 0.2 amps. So we've got 0.1 amp per division. This is set to 100 millivolts per division. So let's see if we turn down the brightness on the monitor whether we can see the amplitude here change. So the front panel displays have stopped responding a little bit here. So the front panel doesn't seem to be working properly at the moment. I can't even turn the monitor off. So I'm starting to wonder if maybe there is something on the secondary side of the power supply which is causing this not to work properly. I'll just cycle the mains power to the monitor. So now this doesn't seem to be powering up at all. I've just checked. Oh no, it's going now. Wow, that is drawing a horrible waveform from the mains. Let's have a look at that on the oscilloscope. So just as I move the camera up to the oscilloscope, it seems to be drawing a more normal waveform from the mains. But the front panel controls are definitely not working properly at all. It's basically not really responding, and I'm beginning to wonder if there's something wrong on the secondary side of the switch mode power supply that's causing all the low voltage electronics to glitch out. So it could be that it's just as simple as the smoothing capacitors on the secondary side have dried up. So I didn't check any of those, I only checked the primary side. And I'm beginning to wonder if it wasn't powering up because there was something up with the power supply, and the overloading issue is an unrelated issue. So let's have another look inside the monitor and have a look at those capacitors and the power supply again. So I've taken the back cover back off the monitor. I've plugged in the VGA cable and the power cable again, and I've got the Fluke 87 set to DC volts. The monitor's connected through the isolation transformer, but this is still energised, and there's a lot of charge being stored in some of these capacitors, so we still need to be really careful here. But I've had a quick look at the bottom of the PCB, and it looks like we've got about 5 ground wires, but we can take our ground off the chassis. So I've just buzzed this out between here and the chassis, and we're getting 0 ohms continuity. And then we've got the 2 wires at the bottom, which are one power supply rail, and then the next 2 further up are the other power supply rail. So let's turn on the monitor. So we've got mains coming in now. And the monitor's turned on, so I can just about see the green LED. So this is now drawing power. It's drawing 31 watts. And if we have a look at the voltage on this pin here, we've got 3.287, so that's supposed to be the 3.3 volt rail. And then the next one up, we've got 4.7, which is our 5 volt rail. So that all seems to be normal. I might just connect the oscilloscope and have a look at what those voltages are looking like on there. So I've just hooked up the Rigol to the power supply. So we've got channel 1 is the 3.3 and channel 2, which is blue, to the 5 volt rail. And these are AC coupled at 50 millivolts per division. So the 3.3 volt rail is really nice and clean, but the 5 volt rail is a little bit more noisy than I would hope that it would have been. But I wouldn't be expecting that to cause any issues with the display in particular. So I think I'm just going to leave it for a moment and see if it warms up and whether that gets any worse. The display is actually constantly doing that auto adjustment, and the menu buttons are completely unresponsive again. So it might be worth just checking the supply voltages actually on this board. There is one electrolytic capacitor on the little digital board, and it might be worth just checking that's okay. But if the power supplies are checking out alright and it's just not behaving properly with the front menu buttons, it's either there's a bit of damage to this wire between the menu buttons and the main board, or there's just something wrong with the main board. So I'll leave it for a bit and see if it gets any worse, and then we'll just have a look at the controller board. So this has been on about 10 minutes now and the waveforms haven't changed, so the power supply doesn't seem to be getting hot in a way that's causing the rails to get worse. So I think I'm just going to check the supply rails actually on the controller board and see if there's anything suspect going on there. It might be worth just checking the ESR of this capacitor that's on the board, but I'm starting to think that we're not going to be able to repair this, and maybe there is just a fault with the controllers that are on the board, because the fact that it's just not responding to button presses very well, although it seemed to start with, which is the slightly odd thing. So when it was first powered up it was behaving completely normally, and then started playing up after it had been on for a short while. So nothing's getting particularly hot, so I've just gone round with the Fluke IR meter, and all the temperatures, it's kind of 35 degrees, 40 degrees. The power supply's about 50 degrees at the warmest point, so nothing terribly warm there. None of the components are really being stressed. So failing this capacitor being faulty that's on the board, I think this may be a lost cause, and given that it's nearly 10 years old, it's probably due to be thrown out anyway. It would have been nice to repair it anyway, but we'll have a look at this and then make a decision. So I'm now just looking at a few of the voltages actually on the control board. So we've got a really nice 5-volt supply rail here. So it looks like it's all okay on this board. And we've got 3.3, which is also pretty clean. So I'm slightly at a loss as to what's going on. I've just probed out some of the buttons to the controller board and they're all working completely fine. And I can't see anything wrong with the soldering actually on the controller board. This is presumably made by a completely different company or a different factory, because the standard is completely different to the power supply. So that all seems to be fine. So I think we may have to give up on this monitor. So I think that's about all we can do for this monitor for today. It's a bit of a shame that I haven't been able to fix it, and even now it's not turning on at all. But the controller board was getting 3 and 5 volts absolutely fine, and actually on the board the rails were really quite clean, so I don't know what's happened to that. The actual menu buttons are definitely working, and I was able to use the meter to check that each of the buttons were working, but it was just continually doing that automatic adjust. And I did try and connect it just now through the DVI connection, and the computer doesn't even pick up that there's a monitor there anymore. So there's obviously something wrong on that controller board. So I think that's about the end of this monitor, and I'll probably salvage some parts out of the power supply, and then I think it's time to send it to the scrap heap. So the fact that it was blowing mains fuses is slightly confusing, and I'm beginning to wonder whether the mains lead was just slightly faulty. So the next time I go round I'm going to check that power cable, because it seems slightly odd. It wasn't drawing anything particularly abnormal in terms of power consumption. I did notice that occasionally when you turn it on for a couple of seconds there were some really big peaks in current, but the average power was still quite low, and a fuse in a mains plug is not going to respond to a small 20 millisecond peak. It's going to be averaged over a small period of time so that the fuse wire can actually melt. So I do think possibly that something was wrong with the mains lead, and the fact that it was unplugged long enough maybe to replace the fuse meant that the monitor was able to power on the next time. But there wasn't any smells mentioned or any smell of burning, so it seems slightly odd that it would be blowing 5 amp fuses that were in the plug. So I think that's about it. So I hope you enjoyed this video. It's a bit of a shame that we didn't manage to fix it, but we got to have a look around some of the parts and have a little look at the switch mode power supply theory. So if you enjoyed this video, please give a thumbs up. Don't forget to subscribe if you haven't already, and thanks for watching.